Good morning, everyone. I am Sindhu and I am pursuing BTech in Electrical and Electronics Engineering at RGUKT RK Valley. It gives me great pleasure to present my internship project titled Real Time Electric Vehicle Dashboard and ADAS Warning System. This project was carried out as part of my Embedded Systems internship at MXZ. During this internship, I gained practical knowledge in embedded C programming, STM32 microcontroller programming, automotive embedded systems, sensor interfacing, UART communication, timer configuration, ADC program, and real-time application development. In this presentation, I'll explain the project objective, hardware setup, software implementation, code architecture, ADAS functionality, simulator demonstration, and finally, the knowledge and skills I have gained through this internship. The MXZ internship was designed to provide practical exposure to embedded systems and automotive software development. Throughout this internship, I learned how embedded systems is developed using STM32 microcontroller and STM32 HAL library. Instead of only studying theoretical concepts, I implemented a complete electrical vehicle dashboard integrated with advanced driver assistance system features. During this internship, I learned how to configure GPIO, ADC, timers, UART communication, interrupts, and modular software architecture. This project was implemented using STM32 Cube IDE, simulated using PixSimLab, and the real-time vehicle parameters were displayed through a Python dashboard system. The primary objective of this project is to design and implement a real-time vehicle dashboard integrated with advanced driver assistance features. The STM32 microcontroller continuously receives input from different simulated sensors including accelerator pedal, brake pedal, battery SOC, motor temperature, and three ultrasonic sensors. Let me show you the connections. So these are the potentiometers used for these pedals and the three ultrasonic sensors for calculating the front, left, and right distances. And these are the warnings, and this is the virtual terminal for our readings. Let me continue with my presentation. This slide shows the hardware simulation setup used for my project. Since the internship is simulated based, I use a PixSimLab, which provides a virtual STM32 hardware environment. The central controller of the system is the STM32F103C86, commonly known as the Blue Pill. Four potentiometers are connected to simulate the vehicle inputs. PA0 represents the acceleration pedal, PA1 represents the brake pedal, PA2 represents the battery SOC, and PA3 represents the motor temperature. In addition, the three HC-SR04 ultrasonic sensors are placed at front, left, and right sides of the vehicle. These sensors continuously measures the distance between the vehicle and the nearby obstacles. And the four LEDs are also connected to indicate the different warning conditions such as collision alerts and blind spot detections from left side and blind spot detection from right side. Finally, the UART communication is established between the STM32 and the Python dashboard to display all vehicle information in real time. This project was developed using STM32 Cube IDE. STM32 Cube IDE provides an integrated environment for configuring peripherals, writing embedded C code, compiling the application, and debugging the program. In this project, several peripherals were configured. The GPIO peripheral is used to control LEDs and interface with the ultrasonic sensors. The ADC peripheral reads analog input from the potentiometers and represent the accelerator, brake, battery SOC, and motor temperature. UART1 is configured for serial communication between the STM32 and Python dashboard. Timer 1 generates the periodic interrupts using the real-time processor, and timer 2 is configured with the microsecond resolution for ultrasonic sensor distance measurement. Timer 3 is used for periodic sensor updates and scheduling. Instead of directly programming hardware registers, the project uses the STM32 HAL, which means Hardware Abstraction Layer Library, which simplifies the peripheral programming and improves code readability and maintainability. Let me show you those configurations. These are the configurations for timers. We use timer 1, timer 2, timer 3, and those all. And we also set the parameters and connectivity, which is the UART we use it, that is for UART serial communication. And this is the pin configuration. We added those pins for input and output uh, processings. Let me continue with my presentation. So this diagram tells the overall architecture of the project. First, the STM32 microcontroller collects the input data from the accelerator brake, battery, motor temperature, and ultrasonic sensors. The EV control module processes these inputs and calculates vehicle parameters such as speed and battery status. The processed data is then passed to the ADAS module, which analyzes the vehicle surroundings and generates safety warnings when required. The fault management module continuously checks abnormal operating conditions such as excessive temperature or other fault conditions. Finally, all processor information is transmitted through UART to the Python dashboard, where it is displayed in real time for the user. Next, the system architecture. The system architecture is, as I said before, it collects data from ultrasonic sensors and other things. After then, ADAS module, after then, fault management. Through all these readings, your communication is send the data to the Python dashboard. Coming to the program execution flow. Program execution flow. Now, I'll explain the implementation of the project. The complete execution of the system starts from the main.c file. The file acts as the central controller of the entire application. Its responsibility is to initialize the microcontroller, configure all peripherals, initialize different software modules, and continuously execute the application. Now we see this HAL initialization. The very first function is executed is the HAL initialization, HAL underscore init. HAL stands for Hardware Abstraction Layer. This function initializes the STM32 hardware library. It configures the flash memory, system tick timer, and prepares the microcontroller to use all HAL functions. Next, the clock configuration. After HAL initialization, the clock system is configured. Every peripheral like ADC, UART, and timers depends on the system clock. Proper clock configuration ensures accurate timing throughout the application. Let me show you our clock configuration. So this is the clock configuration we used in this project. Next, the peripheral initialization. So GPIO stands for General Purpose Input Output. In our project, GPIO pins are used for LED indications, ultrasonic trigger pins, ultrasonic echo pins, digital control signals. And this is this is for defining ADC. The analog to digital converter is initialized. In this project, ADC continuously reads analog values from potentiometers. Those potentiometers simulate acceleration pedal, brake pedal, battery SOC, and motor temperature. The ADC converts analog voltages into digital values ranging from 0 to 4095. Next, UART initialization. This is for UART initialization. UART stands for Universal Asynchronous Receiver Transmitter. It is responsible for serial communication. Our project uses UART to transfer processed vehicle data from STM32 to the Python dashboard. Every speed value, battery percentage, and warning message is transmitted through UART. Next, timer 1 initialization. Timer 1 is configured to generate periodic interrupts. These interrupts allow the application to perform calculations and fixed time intervals. Instead of continuously checking time inside the loop, the timer generates interrupts automatically. This improves timing accuracy and makes the software suitable for real-time application. And this is the timer 2 initialization. Timer 2 is configured with microsecond resolution. It is mainly used for ultrasonic measurement since the HCSR04 sensor measures echo pulse width in microseconds. Timer 2 provides the required timing precision. And finally, this is the Timer 3 initialization. Timer 3 is responsible for periodic sensor updates. It helps refresh vehicle parameters and maintain smooth dashboard updates. Next, starting timers. This is the starting timer initialization for timer 1. This starts timer 1 in interrupt mode. The interrupt is generated automatically after every configured time interval, and this is for timer 3. Similarly, timer 3 interrupts is started for periodic updates, and this is for timer 2. Timer 2 starts in normal mode, but because it is used for measuring ultrasonic echo duration. Next, the module initialization. EV module. This function initializes all electric vehicle parameters such as speed, battery, acceleration, and temperature. Next, ADAS initialization. It initializes all ADAS variables and warning states. Next, ultrasonic initialization, which configures the ultrasonic sensors, and fault initialization. Um, it initializes the fault monitoring system. Next, finally, the infinite loop. After completing all initializations, the program enters an infinite loop. Embedded systems never terminate like normal desktop applications. Instead, they continuously monitor sensor and respond to events through the vehicle operation. Next, what is inside while loop? During every execution, during every execution, the STM32 first reads all analog inputs, then it updates vehicle parameters such as speed, battery. Next, it measures obstacle distance using ultrasonic sensors. The ADAS module analyzes these values to detect possible hazards. The fault module checks whether any abnormal operating conditions are present. Finally, all processed information is transmitted to the Python dashboard through UART. Next, EV control module. The next important module is EV control.c. This module is responsible for calculating the dynamic behavior of the electrical vehicle. This is the workflow of this control module. The first task of module is to read analog sensor values and from the ADC. This includes accelerator pedal, brake pedal, battery SOC, and motor temperature. If we come to the accelerator potentiometer represents the driving throttle input. Higher ADC value means the accelerator pedal is pressed further. This value is converted into an accelerator percentage. Brake. Similarly, the brake potentiometer is converted into a brake percentage. Increasing brake input reduces the vehicle speed. Battery SOC, which represents the state of battery. As the battery level decreases, the dashboard reflects the remaining charge. This parameter is useful for estimating the available driving range. And finally, motor temperature. Motor temperature is continuously monitored. If the temperature exceeds the safe operating limits, the value is forwarded to the fault management module for further action. These I'll show in the dashboard update. Next, the ultrasonic sensor. This is the workflow of ultrasonic sensor. Now I'll explain the ultrasonic sensor module, which is responsible for measuring the distance between the vehicle and nearby obstacles. In this project, I have used three ultrasonic sensor for front, left, and right. Using three sensors allows the system to monitor obstacles in multiple directions instead of only detecting objects directly in front of the vehicle. This is how the sensor works, and I mean, this is the working flow of the sensor. The HCSR04 sensor, which is ultrasonic sensor, works using ultrasonic sound waves. From first, the STM32 sends a 10 microsecond trigger pulse to the sensor. After receiving this pulse, the sensor transmits an ultrasonic wave. If the wave strikes an obstacle, it reflected back to the sensor. The echo pin becomes high until the reflected wave returns. The STM32 measures the duration of high pulse using timer 2. Since the speed of the sound is known, the obstacle distance can be calculated from the measured echo time. Why we only using timer 2 is because timer 2 is configured with microsecond resolution. Therefore, timer 2 is ideal for this application. Next, if we come to the first sensor, front sensor, the front ultrasonic sensor continuously checks the distance between the vehicle and the objects ahead. It is mainly used for forward collision warning. And then left sensor. Left sensor monitors obstacles near the left side of the vehicle. It is used for blind spot detection. And then right sensor. Right sensor performs the same function for the right side of the vehicle. The measured distance are continuously updated and sent to the ADAS module. Instead of displaying raw sensor values directly, these measurements are used to make intelligent safety decisions. ADAS module. After obtaining all sensor values, the system enters into ADAS module. ADAS stands for Advanced Driver Assistance System. Its purpose is to improve vehicle safety by continuously analyzing sensor data and warning the driver before any accident occurs. Rather than simply displaying values, the ADAS module interprets the information and generates meaningfully safety alerts. In this, we obtain collision warning, blind spot, overspeed, and driver alerts. Collision warning. The first ADAS feature is forward collision warning. The front ultrasonic sensor measures the distance between the vehicle and the object ahead. A warning message appears on the dashboard and corresponding LED turns on. This helps the driver react before a collision occurs. Next, blind spot detection. The second feature is blind spot detection. The left and right ultrasonic sensors continuously monitor the areas beside the vehicle. If another vehicle or obstacle is detected close to the either side, the dashboard displays a blind spot warning. This assists the driver during lane changes. Next, overspeed. The EV control module continuously calculates the vehicle speed. If the speed exceeds the configured safe limit, the ADAS module generates an overspeed warning. This alert reminds the driver to reduce speed and promote safer driving. And then driving alerts, we know that temperature monitoring, warning priority, all these. Sometimes uh, more than one warning can occur at the same time. For example, the vehicle may be overspeeding while an obstacle is also detected ahead. The ADAS module prioritizes the most critical warning so that the driver immediately notices that most dangerous situation. And next, fault management module. This is the flow of the fault detection and safety management. After implementing the EV control and ADAS module, the next important component is the fault management module. The purpose of this module is to continuously monitor the health of the vehicle. In every modern automobile, is safety of the safety is one of the highest priorities. This module continuously checks different vehicle parameters such as motor temperature, battery level, sensor status, and ADAS warning conditions. The main purpose of this module is to improve reliability. Detecting faults early helps to prevent damage to the vehicle and improves passenger safety. This is one of the most concept used in real automotive embedded systems. And then UART communication. The next module is UART communication module. UART stands for Universal Asynchronous Receiver Transmitter. It is responsible for transferring data between STM32 microcontroller and the Python dashboard running on the computer. After the EV module calculates vehicle parameters and ADAS module generates warning messages, all this information must be displayed to the user. Therefore, STM32 sends the processed data through UART. The Python application continuously receives UART message. It processes the incoming data and updates the dashboard in real time. This allows the user to visualize all important vehicles while the simulator is running. Why only we use UART? UART is simple, reliable, and widely used in embedded systems. It allows microcontroller to exchange information with external applications without regarding complex communication protocols. And this is the Python dashboard. It is the final overview of the final demonstration slide of our dashboard system. Let me show you the final demonstration of my project. This is the main.c where we included all those files and initialization is all occurred here. And this is the IOC file, our pin configuration. This is the configuration of pins for STM32. And this is the clock configuration where we used these in UART and ADC modules. And let me show you the Pixim lab. This is the Pixim lab. Here we can select the board as blue pill and it added microcontrollers and modules, spare parts, which we are connected to the project. And these are the 4 potentiometers used for acceleration, brake, SOC, and the temperature. And these are the 3 ultrasonic sensors which are responsible for calculating distance between the vehicle and the obstacles. And these 4 LEDs are responsible for the collision, blind spot detections. And this is the virtual terminal, which continuously shows the parameters, updated parameters of the vehicle. Let me show you. So this is the readings of updated parameters: speed, SOC, torque, range, acceleration, brake, and the front distance, left distance, right distance, time to collision, and these. Let me go with the Python dashboard. For that, we need to open command window, run as administrator, and copy the file of Python code where we are placed and just enter it. So this will show the main dashboard of this project of the vehicle parameters. So this is the EV ADAS dashboard. By changing the acceleration, brake, SOC, by increasing the acceleration, the speed also increases gradually. Just look at it. By applying the brake slowly, the speed gradually decreases. It takes time. Now it is gradually decreasing. And this is the battery percentage. And these are the readings like torque, acceleration, brake, motor temperature, alarm, false. This is the speed history. It is gradually decreasing. And this is the bird view of our vehicle. We can also as the obstacle come closer, alarm is on. Blind spot detected and alarm also advised. So this is the final demonstration and final look of the project, and those are the parameters which have been shown. And thank you so much for giving this opportunity to let me explain what I have learned through this internship and what my output looks like. And finally, so this is what we have implemented, and thank you.